Hey, what's going on, fellas? Today we're melting some cast iron using waste vegetable oil. A customer of mine has told me he's going to be using this as a fuel, and today we want to find out which is faster. Is it quicker to use waste oil to melt metal? Everyone says it's hotter and has more BTUs. It does have more BTUs, but it's not hotter. It does take longer than the diesel fuel did, and we're going to see that today, so let's check it out. All right, fellas, we're back here at White Sands Proving Grounds doing a little job for Jeremy. He wants to see some waste vegetable oil. I don't have any, so we're just going to go for the good stuff here. It should burn the same. So basically, this is what we got. I wanted to show another little feature that I've used to modify this foundry. I have inside of here a sacrificial stainless steel crucible floor. You can see it down there. And what this does is it glows like almost white hot. It will eventually burn out of there, but I've got so many of them it doesn't matter. And that enables me to heat the very bottom of this crucible far better than just with the fire brick alone, because fire brick is a poor conductor of heat. So not only does it take a long time for it to heat up, it takes, it blocks a lot of energy from actually flowing into the crucible. Not that this one has a lot of surface area on it, but nonetheless, it's better to have your crucible sitting on something that's glowing white hot. So that is a sacrificial piece of kiln furniture, I guess you would call that. Just wanted to share that with you. Now, we have a pound of iron already in here, approximately. And because it's one big solid clump now, it may take longer to melt, simply for that reason alone. When we initially did the test on this, we were able to melt that iron in 8 minutes from a cold start. However, the surface area was much larger at that time. Now we just have a large clump. I'm going to add this piece simply to enable us to observe when we've hit the melting point a little bit better. So we'll set that there. We'll set our crucible in there on the little piece of furniture. And we're going to go for this. Unfortunately, my airflow gauge blew up on me, so we're not going to be able to get any flow rates. It's right around 4 cubic foot per minute at about 70 psi's back pressure. Okay, fellas, I was worried about this. Because the viscosity of oil is so much thicker than water, the turbulence and resistance to flow that's experienced by this weight is a little bit higher. So even though the buoyancy is less than oil, the drag is higher. So the higher drag is giving us a false indication of 1 liter per minute, but I assure you that is not the case. At the end of the test, it appears we burned about a half a gallon in a time span of about 16 minutes. So that's more like 2 gallons an hour, 7.8 liters an hour. 78 kilowatts or 266,000 BTUs. So we're moving right along here. I definitely did not take time to set the flame to an optimum setting. I regret that. We're right about 6 minutes here. Last time we were at 2,400 degrees and melting already. This time we're not that hot. We're right around 1,700 degrees, 2,000 degrees. The small decimal becomes significant on this meter when it goes over 999 degrees. You'll notice the decimal point will disappear. So we're getting there. The total burn time, guys, ends up being like 12 minutes and 58 seconds. Here we are 10 minutes in. And things are starting to liquefy. I can see boiling down at the bottom of the crucible. That one piece is still standing tall. I'm having a hard time seeing it this time around due to the fact that there's a lot more flames coming out of the burner. We need to reduce that in the next test. You don't want flames flying out of the top when you're doing a melt. We're there. We are at the melting point of cast iron pretty much. And we are 11 minutes and 33 seconds in. Things are doing pretty good here. We're still screaming right along at high speed. We did it in 8 minutes last time with diesel fuel. That was complete liquefaction of the metal. And our crucible has failed on us, unfortunately. That big blob that you see at the bottom is actually a plug of 3,000 degree refractory that was used to seal the bottom of that crucible. That is not a lump of iron in the bottom of that. We'll be taking a look at that here in a second. But for the most part, we've got some kind of concrete thermite reaction going on down inside of there. Check that out. That one piece is just really blistering. It's white hot too. So we're definitely very hot there. That's pretty incredible. You can see the little bit of melted iron is that yellow stuff. That red stuff is the refractory material for the most part. I'll show you that here. Let's take a look at that and you'll see what I'm talking about. All right, so everything was melted when I went to see where my poker rod was. I just seen this muffin thing in the bottom of the crucible thinking it wasn't melted yet when everything had already drained out onto the floor. So we definitely hit a melting point. The crucible was destroyed. I am going to do the test again one more time using this crucible because I'm interested to see how well these perform. I'll leave a link in the description for this crucible in the event that it works. I basically just wasted a good burner nozzle here on this, but nonetheless I had to see it in action. These things aren't as resilient as I had hoped. Not sure why this cracked on us like that. Okay, we're going to try this again. We have 370 grams of cast iron. This time I'm going to try to dial the flame down to more of a lean burn. So there it is, big chunk of iron. It welded itself to my pan, unfortunately. I tried to get it out of there. It's strangely enough welded pretty good. Who would have thought? I would imagine it would just peel right off of there. The crucible seems to have been dissolved by the liquid iron. Look at that. This is a silica crucible. And as far as I know, they do add silica to foundry mixes of iron. So it makes sense. Other than that, it held up great. Didn't crack or break. And I think I know why this one broke. We filled it up with liquid iron and then let it solidify. Well, I bet when we heated that clump of iron back up, that it expanded inside the crucible and caused it to crack. That's my theory anyway. All right, Jeremy, so if you're still with me, we are going to be doing another test for you tomorrow for your firebox turbulence testing. Let me show you what I got in mind here. Right here, we are going to either try the cyclone configuration or, as you have depicted in your diagrams, the two burners facing downward. Of course, this distance here would have to be considered based on your diagrams, and I may even modulate that, testing it at different heights. I am concerned that this particular setup is going to cause turbulence and entrained flow of combustion gases of the other flames that kind of inhibits combustion and causes poor performance. I may take two blow torches and aim them together to kind of show you this. And I've learned this from also trying to solder large pieces of copper. I would often get out two blow torches, and sometimes I've noticed if you hold one flame too close to another, you can actually almost extinguish them both. A lot of it has to do with entrained flow. If we do the cyclone configuration, not only does this not happen, but the residence time of the combustion gases is a little bit longer, so you get a little bit more of an efficient burn, and your exhaust velocities are a little bit more lazy. I don't know. We'll check it out. We'll see what happens. This is possible. It may just end up causing a feather flame that faces downward. But even so, I'm worried about this kickback that's going to take place right here. You're going to have this area in here that's going to fill up with carbon monoxide, or carbon dioxide, I'm sorry, and other like nitrogen contamination. And it's going to mess with the flame. It may not happen, but I've seen this in the past. Buffeting and all kinds of strange things can happen. And secondly, when you go to light one torch, okay, you're going to have fire just blasting and breathing all over the other torch, which is going to come out this side. Sorry for not having a red pen handy. I threw it. It broke on me. Anyway, that's pretty much the gist of it. I'm worried about igniting one and you got fire shooting out the other, and just the nitrogen and CO2 contamination getting caught in this corner is going to get caught up in that flame, and entrained flow is a big deal for combustion. You don't want that. You have to have fresh oxygen coming around that at all times, and you kind of get that here because we have that secondary air system that's going to be pulling air around the flame for a while. Even though there's two flames in here, they actually envelope each other with air, so it's not quite the same starvation. There's no turbulence where you have little fireballs just burning up all the oxygen and producing a bunch of gas in this little area that ends up in the big flame, which then causes large flames to shoot out the top, and you're wasting all your fuel and energy. I'm just gonna babble forever, so I'm gonna shut up and I'll holler at you guys later.